In this session, we are going to first discuss the basic definition of a partial differential equations. After that, we are going to see some common types of partial differential equations and their applications. After that, we are going to see how we are going to derive a partial differential equation by eliminating arbitrary constants and arbitrary functions. These are the things we are going to discuss in this session. First, we will see what is the basic definition of a partial differential equation. The definition first. What is the definition of a partial differential equation? A partial differential equations are those which involve one or more partial derivatives. Partial differential equations are those which involve one or more partial derivatives. This is the definition of a partial differential equation. It is an equation which involves one or more partial derivatives. For example, a simple examples we are going to see now. If suppose a function u which depends on three independent variables x, y, z, then dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square equals to 0. It is also known as, this equation is known as a Laplace equation. We give the name for this, Laplace equation, and this is a partial differential equation. And because there are terms involving partial derivatives, and it is a second order PDE. The order of a differential equation is already discussed in ordinary differential equation. Same thing. The highest order present in a differential equation is 2. So the order of this differential equation is 2. Then we have, let us see, suppose this is the first example, and the second one, if suppose there is a variable z which is a function of two variables x and y, then dou z by dou x plus dou z by dou y plus dou z by dou x into dou z by dou y equal to 0 is a partial differential equation. Suppose, for simplicity, we are going to denote, let p equals to dou z by dou x and q equals to dou z by dou y, and I simply just write r equals to dou square z by dou x dou y, and s is equals to, r is dou square z by dou x square, and s is dou square z by dou x dou y, and t is dou square z by dou y square. Now these are the notations we will be using it in our study. We are going to restrict our study to only two independent variables, say x and y, and this z is an dependent variable. And these are the notations we will be using it, p, q, r, s, t, and these are the partial derivatives, first and second orders. So this differential equation, what is written in 2, I can write it as, that is, we can write it as dou z by dou x is p plus dou z by dou y is written as q plus pq, and this is the PD using the notations given above. These are the standard notations will be used in our study. throughout the chapters we will be using this p, small q, r, s and t. This is the meaning, and these are the examples. And one more thing I can give, suppose v is a function of two other variables x and y, then dou square v by dou x dou y equals to 0 is also a PD. Sometimes this can be written as Vxy equals to 0. This is a simplified version of this partial derivatives. V suffix xy equal to 0. Suppose dou z by dou x means, suppose dou z by dou x, I can write like that. Z differentiated partially with respect to x. Dou z by dou y, we can write it as z partially differentiated with respect to y. These are the standard notations will be used throughout the chapter. Okay, and these are some examples. And now we are going to see some common types of partial differential equations. Some common types of partial differential equations and also their applications. The first one is the heat equation. They give the name for the differential equation. And this heat equation was derived by Joseph Fourier. Joseph Fourier. The heat equation, and so what you can see is this Joseph Fourier is a French mathematician and a physicist, and he is the person responsible for the development of the Fourier series formula, and which eventually developed into Fourier analysis and harmonic analysis. And he is the person who derived this heat equation, and it has a very wide applications. First, I'll write what is a heat equation in 3 dimensions. That is, dou u by dou t equals to alpha times dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square, where this u is a function of x, y, z and t. X, y, z is a point in 3-dimensional space, and t is a time. So this function depends on the position as well as the time. And what is alpha in this? Where alpha is the thermal diffusivity. Thermal diffusivity of the medium. The thermal diffusivity of the medium, and this u is the temperature at any point x, y, z and at a time t. So u denotes the temperature at any point x, y, z at time t. The above equation describes the flow. The above equation describes the flow of heat describes the flow of heat in a homogeneous and isotopic medium. Medium in the sense it may be pure water or glass, even air also. This is a homogeneous medium, means an optical medium which has a uniform composition throughout. We call it as a homogeneous medium. So like this medium, if this equation describes the flow of heat in a homogeneous and isotopic medium. These are the restrictions for this heat equation. It should be homogeneous equation, homogeneous medium with this U, X, Y, Z and T being the temperature at the point X, Y, Z and at time T. So now I am going to share you the solution of a partial differential equation, this heat equation. That is a solution of a heat equation, and you can just see the geometrical meaning of that. I'm going to share that file. Yes,